Welcome to the Deep Dive. Today we're taking a really fascinating journey into the mind of one of history's greatest mathematicians, Terence Tao.
Often called the Mozart of Math.
Right, exactly. He's a Fields Medalist, Breakthrough Prize winner. I mean, his work spans an incredible range of fields in math and physics.
Truly astonishing breadth.
And our source material for this deep dive is this profound conversation. It really unpacks some of the toughest problems out there. Math, physics, even touches on the future of AI.
Sounds like quite a discussion.
It is. So our mission here is basically to give you a shortcut, to pull out the key insights, the most important nuggets from this discussion.
Making these really complex ideas a bit more accessible and hopefully exciting too.
Precisely. So let's dive right in. Tao starts off by defining what he sees as genuinely difficult problems at the research level.
Okay.
And he's not talking about problems that are just arbitrarily hard or, ones we already know are unsolvable.
Right. Not just mathematical curiosities.
No. He points to the ones on the boundary, that's his term, where our current techniques can get us maybe 90% of the way there.
Ah, okay.
But that last 10%, that final step, is just completely elusive.
That's a great way to put it. So what does that really mean for how mathematicians work? Is it just banging your head against the wall, or is there something specific about that boundary?
Well, it seems like it's often about waiting for that breakthrough, that aha moment for the last 10%.
Yeah.
It requires a totally new idea, right? Conceptual leap.
Gotcha.
He gives the Kakeya problem as an example. It started out as this simple puzzle back in 1918 from a Japanese mathematician, Soichi Kakeya.
Okay. What was the puzzle?
How do you turn a needle around a full 360 degrees using the smallest possible area?
Huh. Sounds simple enough.
In 2D, yeah. Another mathematician, Besikovich, came along and showed something really surprising. You could actually do it with, quote, as little area as you wanted, like 0.001 or even less, arbitrarily small.
Wow. Okay. So basically zero area.
Effectively, yeah. But then things get much more complex when you jump to 3D.
Right. 3 dimensions always complicates things.
Totally. So imagine you have a really thin object, maybe like the Hubble Space Telescope, right? And you want to rotate it so it points in every possible direction. But you want to do that while making the volume. It sweeps out as small as possible.
Minimum possible volume.
Yeah. And the conjecture, the guess, was that this minimum volume would shrink very, very slowly as the object got thinner. Logarithmically slow.
And was that proven?
It was, yeah. After a lot of really hard work, that was confirmed.
That's pretty wild for what started as a puzzle about a needle. But, okay, how does rotating a telescope in minimal space connect back to physics? Like waves or something. Seems like a big jump.
It does seem like a jump, but that's the amazing part. It's a really surprising connection. Think about wave propagation.
Okay, like ripples in a pond.
Exactly. You have wave packets, these sort of localized waves moving through space and time. They occupy a region, kind of like a tube. Now, the equations allow you to run time backward. So instead of ripples spreading out, imagine them converging, focusing intensely at a single point.
Ah, focusing energy.
Right. And that could potentially cause what's called a singularity or a blowup. The amplitude gets infinite maybe. The Kakeya conjecture, surprisingly, is deeply connected to understanding whether and how waves can concentrate like that.
So it tells us about the limits of wave focusing.
In a sense, yes. It helps understand if certain fundamental physics equations can even allow these intense singularities to form. It's crucial. And this idea of singularities brings us neatly to another huge boundary problem, maybe one of the most famous unsolved problems in mathematical physics.
Uh-oh. Sounds important.
It is. It's the Navier-Stokes regularity problem, one of the 7 Clay Millennium Prize problems.
The $1 million one.
That's the one. These equations, Navier-Stokes, they govern fluid flow, water, air, crucial for things like weather prediction.
Right. Basic fluid dynamics.
Well, yes and no. The core question is this. If you start with water flowing smoothly, can its velocity ever concentrate so much at a point that it becomes infinite? A singularity.
Does that actually happen? Like, does water just explode?
Yeah, no. Tao points out we definitely don't see that in real life. But mathematically, it might be possible. And actually, the consensus among mathematicians seems to be shifting towards, yeah, it could be possible, but only for very specific, carefully engineered starting conditions.
Okay, so why is this particular set of equations so incredibly hard to understand? Fluid flow seems common enough. What makes proving things about it worth $1 million?
It boils down to something Tao compares to Maxwell's demon.
Okay, the thought experiment.
Yeah. Just like a demon could theoretically unmix gases against probability or find a hidden pattern in pi, there's this idea that a kind of mathematical demon could keep pushing the fluid's energy into smaller and smaller scales.
Forcing it to move faster and faster.
Exactly. Faster and faster, potentially leading to what's called a finite-time blowup.
Yeah.
All the energy concentrates at one point in a finite amount of time.
But viscosity usually stops that, right?
No.
Spreads the energy out.
Normally, yes. Viscosity acts like friction, damping things down. But the demon in this scenario finds a way around it, theoretically. Now, Terence Tao himself did some really groundbreaking work here. In the Conda 16 paper, I think the title was something like Finite Time Blowup for an Average Three-Dimensional Navier-Stokes Equation.
Averaged, so not the real equations.
Right. He couldn't prove it for the actual equations. He said they were just too complicated. So instead, he basically engineered a blowup. He changed the rules.
Wow.
By simplifying the physics. He said he, quote, turned off certain types of ways in which water interacts and only kept the ones that I want. He forced it to blow up in this modified artificial system.
Okay, engineering a blow-up in a fake system sounds, well, interesting, but how does that help with the real problem? Does that artificial blow-up tell us anything useful?
It absolutely does. It provides what mathematicians call an obstruction.
Obstruction?
Yeah, because his artificial equation does blow up. It means any proof trying to show that the real Navier-Stokes equation never blows up, that it has global regularity, must rely on some specific feature of the true equations that his artificial one lacks.
Ah, I see. So it rules out certain types of proofs that would also work for his simplified model.
Exactly. It saves potentially years, decades even, of mathematicians barking up the wrong trees. It narrows down the possibilities. And his work really highlights this concept of supercriticality.
Supercriticality.
Think of it like this. In 3D fluid flow, as you look at smaller and smaller scales, the forces causing instability, the nonlinear transport terms, they get much stronger, much faster than the stabilizing forces, like viscosity, the linear dissipation.
So things get inherently wilder at smaller scales.
Pretty much. It's like trying to balance something that gets exponentially more wobbly the smaller it gets. This imbalance, this supercriticality, is why 3D Navier-Stokes is so much harder than the 2D version.
And 2D doesn't blow up.
No. Ladies-in-Sky proved that back in the day. In 2D, the forces are critical. They stay balanced, it's stable. But 3D is supercritical, unstable, unpredictable.
Which is why weather forecasting is so hard past a couple weeks.
That's a big part of it, yeah. That inherent unpredictability at small scales blows up, metaphorically speaking, over time. But then Tao took this idea from his blow-up construction and went somewhere truly mind-bending.
Where did he go with it?
He started thinking. Well, his construction required carefully programming how the energy funneled down. So he wondered, could the laws of water themselves actually support computation?
Wait, computation? Like a computer made of water?
Exactly. The idea of a liquid computer or a fluid Turing machine.
Whoa.
Instead of electrons carrying bits, imagine pulses of water, colliding in just the right way to create logic gates. And D gates, or R gates, built from fluid dynamics.
That's wild.
He said you could chain these together, theoretically, to make a Turing machine. A water punk computer, he called it. He even drew this analogy to a von Neumann machine.
A self-replicating machine.
Yeah, a self-replicating fluid robot that transfers all its energy to a smaller copy of itself, powers down, and the new, smaller machine continues the process, shrinking down and down, faster and faster, leading to that finite-time blowup.
Okay, that's an incredible conceptual leap. From fluid blowup to self-replicating water robots. Is there any precedent for linking physical systems and computation like that in math?
There is, actually. He mentioned cellular automata, like Conway's game of life.
Ah, the simple rules, complex patterns.
Right. Simple rules, but you get these incredibly complex structures, emerging gliders, glider guns, things that can even form logic operations. That inspired him. It showed that if the underlying mathematical form is similar, you can find these deep connections between seemingly totally different areas.
So the math structure is the key link.
Yes. But, and this is crucial, he stressed that these complex computational structures, whether in the game of life or hypothetically in fluids, they only emerge from very carefully prepared initial conditions, not from random sloshing.
Right, you have to set it up just perfectly, not random noise.
Exactly. And that insight loops back to Navier-Stokes, too. A blow-up, if it exists, probably requires a very specific, non-random starting state. It highlights this big theme in math, the difference between structure and randomness.
Structure versus randomness.
Yeah. He also brought up the infinite monkey theorem. You know, given infinite time, monkeys randomly hitting keys will eventually type Hamlet.
Right. Infinity allows anything, eventually.
Pretty much. Tao notes that infinity is mathematically useful. It absorbs a lot of sins and can simplify things. But for real-world problems, it's often better to finitize things, turn infinite statements into concrete, quantitative ones. Makes them more intuitive, even if the math gets, as he put it, much, much messier.
Finding that practical middle ground between elegant infinities and messy reality.
Exactly. So, okay, how does all this relate to how mathematicians actually solve these monsters? Tao has this philosophy he calls cheating strategically.
Cheating? Sounds fun.
It means changing the rules slightly. Simplifying a hard problem by deliberately turning off most of the difficulties. You solve the simpler versions first, tackling the difficulties one by one.
Break it down, isolate the hard parts.
Right. And he argues this whole philosophy is now getting supercharged by AI and computer-assisted proof systems.
Ah, technology entering the picture.
Big time. He talked about a system called Lean. It's a formal proof programming language.
Formal proof language. What's different about it?
Unlike regular code, Lean doesn't just run, it produces certificates. These are essentially 100% mathematically guaranteed proofs for every single tiny step. The computer verifies everything.
Okay, but what's the practical difference? If it takes, say, 10 times longer to write a proof in Lean than on paper, what's the big advantage?
That's the trade-off. He described using Lean as like explaining a proof to an extremely pedantic colleague.
Huh. I know the type.
Right. It forces absolute precision, define every object, justify every single step. It's laborious up front, takes maybe 10 times longer, like you said.
So the payoff?
The payoff is huge later. If you need to tweak something, change a parameter, fix a subtle assumption deep in a long proof, the Lean compiler instantly tells you exactly which few lines are affected.
Ah, instead of manually rechecking hundreds of pages.
Precisely.
Yeah.
It saves enormous amounts of time in debugging and modification. It also enables what he called extremely atomic level conversations when collaborating. And it allows for trustless mathematics. You don't need to trust the human, you trust the Lean certificate.
That's powerful for collaboration.
Hugely powerful. He gave an example. His equational theories project involved something like 50 authors working on 22 million algebra problems.
22 million? How's that even possible?
Only possible with Lean. It allowed them to effectively crowdsource the proofs. Individuals could contribute small pieces, and Lean automatically verified each contribution, fitting it into larger structure. Unprecedented scale.
Wow. So with tools like Lean becoming more common, what's the absolute cutting edge for AI and math right now? And where does human intuition still win out?
Well, he mentioned things like DeepMind's AlphaProof. It uses reinforcement learning, and it's gotten quite good at solving, say, high-level high school math competition problems.
Impressive, but still high school level.
Yeah. It struggles with the sheer complexity, the combinatorial explosion of higher-level research proofs. And apparently, solving even one problem can take days of Google server time.
Not quite practical for everyday research, then.
Not yet. Plus, he noted that AI proofs can look perfect on the surface, but sometimes contain really subtle or even stupid errors. They lack what he called the mathematical smell.
The smell test, that gut feeling mathematicians have.
Exactly, that human intuition about whether an argument feels right even before verifying every detail. AIs don't have that yet. However, Tao does think AI could make a really significant breakthrough this decade.
Improving theorems.
Not necessarily proving existing ones, but maybe in generating new, interesting, meaningful conjectures.
Discovering new questions, not just answering old ones.
Right. Right now, AI struggle to discover genuinely new physical laws from raw data, for instance. They often need hints or get contaminated by knowing the answer already. But he envisions AI becoming a true collaborator.
How so?
Evaluating human ideas, running massive computations, checking arguments, maybe even suggesting fruitful directions, helping humans push the frontiers. He joked that AI needs to go through grad school.
Huh. Learn from failure.
Yes. Learn from mistakes, false starts, dead ends. That's crucial for how humans learn and develop intuition, but that failure data is often embarrassing and doesn't get published for AIs to train on. So, okay, AI is changing the how, but the who, the human element, is still central. And speaking of remarkable human mathematicians, Grigori Perelman.
Ah, Perelman, the Poincaré conjecture solution, right. And famously turned down the Fields Medal and the $1 million.
That's him. An incredible story of both genius and, well, unconventional choices.
Can you give us the quick version of the Poincaré conjecture? Why was it such a huge deal?
Okay, basically it's about classifying shapes, specifically curved 3D spaces.
Shapes of universes, potentially?
In a way, yeah. Think about 2D surfaces first. A sphere is smooth, finite, and simply connected. Any loop you draw on it can be shrunk down to a single point without leaving the surface.
Okay, like a rubber band on a beach ball.
Right. But now think of a donut, a torus. It has a hole.
Yeah.
You can draw a loop around that hole that cannot be shrunk to a point. It's not simply connected.
Got it. Whole means not simply connected.
So Poincaré asked, back around 1904, if you have a 3D space that's finite, bounded, and simply connected, no holes you can loop, does it have to be deformable into a 3D sphere?
Intuitively, it sounds like it should be true.
It does. But proving it took a century. A major step was Richard Hamilton's idea of using Ricci flow.
Ricci flow, that
Yeah.
sounds familiar.
It's the inflating a crumpled balloon idea we mentioned. You use an equation to sort of smooth out the wrinkles and curvature of the space over time.
Trying to smooth it into a perfect sphere.
Exactly.
Yeah.
But the problem, especially in 3D, was that the Ricci flow equation itself is supercritical, like Navier-Stokes again.
Uh-oh. Singularities.
Yep. Nasty singularities could form. The space might pinch off into points or develop weird structures instead of becoming a smooth sphere.
So Hamilton's approach stalled.
It hit major roadblocks because of these singularities. Then Perelman came along. His genius was introducing these completely new mathematical tools, these quantities he called reduced volume and entropy.
New ways to measure the space.
Kind of. They acted like special lenses. They allowed him to reframe the problem, turning this scary, supercritical behavior into something more manageable, more like a critical, stable system. It's like finding the perfect coordinate system to make sense of the chaos.
So he could understand and control the singularities.
Precisely. He developed a way to classify all possible types of singularities that could form, and then showed how to perform a kind of mathematical surgery to resolve them, proving that ultimately any such 3D space must be equivalent to a sphere. Monumental work.
Just incredible determination.
Absolutely. It really exemplifies that tenacity. Tao shared his own experiences too, with what he called productive mistakes. Years spent on a problem, hitting dead ends.
But learning something crucial from the failure.
Exactly. Failing, but then realizing later that the techniques developed or the insights gained were key to solving a different problem or revisiting the original one with a new perspective. He also talked about Stiles describing himself as more of a fox, connecting different fields.
Compared to a hedgehog who digs deep into one thing.
Right. And he stressed that math needs both, the deep specialists and the bridge builders.
Makes sense. You need both depth and breadth.
Definitely. Okay, finally, let's touch on maybe the oldest mathematical mystery of all, prime numbers.
The building blocks, the atoms of mathematics.
That's a great way to put it. Addition is easy. Multiplication is easy. But when you combine them, things get incredibly difficult, like the Twin-Prime Conjecture.
Are there infinitely many pairs of primes that are just 2 apart, like 3 and 5, 17 and 19, 101 and 103?
Exactly. Simple question. Nobody knows the answer for sure.
Why is that specific question so hard? We know primes go on forever. We know other patterns, like the Green-Tao theorem you mentioned earlier.
The Green-Tao theorem showed primes contain arbitrarily long arithmetic progressions, like 3, 7, 11, add 4, or 5, 11, 17, 23, add 6. Any length you want, you can find it somewhere in the primes.
So why are twin primes so much harder than arithmetic progressions?
Tao explained that the twin-prime conjecture is incredibly fragile.
Fragile? How so?
Imagine you could just delete a very, very tiny fraction of all the prime numbers. Carefully chosen ones. You could potentially destroy all the twin prime pairs, making the conjecture false.
Without really changing the overall statistics of prime.
Right. The overall density, the distribution, and progressions might look almost identical. This means any proof for twin primes has to be incredibly subtle and delicate. It can't just rely on broad statistical arguments.
It needs to capture something very specific about the fine structure.
Exactly. There's something called the parity barrier, which basically says our current methods are too coarse.
Yeah.
They can't reliably distinguish between numbers with an even number of prime factors and those with an odd number in certain situations, which turns out to be crucial for twin primes.
Whereas the arithmetic progressions are more robust.
Yes. Tao described those patterns as being like cockroaches.
Huh. Cockroaches.
Yeah, they show up everywhere. Whether the set of numbers looks random or structured, those arithmetic progressions tend to appear. They're statistically resilient, making them easier to tackle with existing methods. And just as a final quick mention of simple but hard problems, the Collatz conjecture.
Oh, right. The 3n plus 1 problem. Start with a number. If even, divide by 2. If odd multiply by 3 and add 1, does it always end up at 1?
That's the one. Sounds like a game, right?
Yeah.
But proving it always reaches 1 is, again, extraordinarily difficult.
Because the sequence jumps around unpredictably.
Totally chaotic for some numbers. Tao himself made progress, showing statistically like 99% of numbers do tend to drift downwards towards 1, but proving it for every single number, that last 1%, that's the killer. Another simple-looking problem, hiding immense depth. So quite a journey we've taken. We've looked at these really profound challenges from Kakeya to Navier-Stokes.
Saw those surprising links to fluid computing.
Witnessed how AI and new tools like Lean are changing how math gets done.
And touched on the sheer human brilliance behind breakthroughs like Perelman's.
Exactly. So hopefully you now have a better feel for the kind of ingenuity involved, both human and increasingly artificial, that's pushing the limits of what we can grasp about the universe.
It really is a testament to curiosity and perseverance, isn't it? Now amplified by these new tools.
It really is. And maybe we can leave you with this thought, something Galilei said, which was quoted in the source material. Mathematics is the language with which God has written the universe.
A classic quote.
Indeed. So consider this. As our ability to read and maybe even shape that language improves with human insight and these powerful new tools, how might that fundamentally change our understanding of reality itself? Something to ponder.